We're going to shift gears now to something that's very different from the filters we've looked at in the past, which basically are gradient descent filters, recursive least squares, and then the Kalman filter. Now we're going to switch to particle filters. To understand how this is different, we should note that the Kalman filter is essentially tracking a Gaussian distribution through a system. We keep track of our expected state, and we keep track of our uncertainty. And we have measurements in which we have our expected value and our uncertainty with the measurements. And with all of those, we keep track of essentially the first moment, or the mean, and the variance. That isn't to say that the distribution we're tracking couldn't be something other than Gaussian, but since we only have the mean and the variance, the Gaussian is the best fit, and so that's basically how things are assumed. Well, what happens if we have multimodal data? In other words, data that has a distribution described by more than one peak, or any other Gaussian function. Or what if our system is nonlinear and difficult or impossible to model in a convenient way, as we've looked at? In this case, we're going to switch to something completely different from what we've seen, and it is particle filters to the rescue. So let me give you an example of where something like this may come up. Admittedly, this is kind of simple, but assume that we are trying to track a moving object. Looks kind of like a Dr. Seuss car, but that's okay. And we have a park bench, and we have a tree. So we have some object detector of some kind. Who knows? Maybe it's radar, maybe it's LiDAR. Whatever it is, it will detect that there's an object here, and one here, and one here. However, in this example, we want to track a moving object, the car. Well, we don't have anything to tell us where the car is. And so initially we will have three hypotheses as to what the object we want to track is. If we were to look at these positions and find the average position and the standard deviation, then we would get something like it's going to be hard to draw. A very shallow Gaussian. And this is what our Kalman filter would try to track. Probably not the best approach. Instead, particle filters are going to attempt to estimate the state of the system in kind of a Monte Carlo type manner through observations and modeling of system dynamics. So nearly everything about this statement applies to Kalman filters, but there are a few differences. First, we are estimating the state of a system. That's exactly what a Kalman filter is trying to do. Second, we have observations, just like with our Kalman filter. Next, we model system dynamics, again, just like the Kalman filter. But the difference is that we're going to be doing this in a Monte Carlo type manner. So, and actually, more accurately, we're not so much estimating the state of the system, although that's the ultimate goal, as we're attempting to model a distribution of the state of the system. From a distribution, we of course can come up with whatever system estimate we want to do. So the Kalman filter proceeds in 4 steps that we will repeat some of these steps. So first, we're going to represent distributions by particles, where actually the density of the particles in a particular area approximates that distribution. And just to be clear, put this in plain English. When I say we're representing the distributions, what am I really talking about? The distributions are our estimate of the likelihood of a particular state. So to use our previous example, we're going to start out before we make any measurements. We haven't done that yet. And we're going to have a distribution of particles like this. So this distribution before any observations is going to essentially be a uniform distribution, telling us that we have no idea where anything is. So just a little bit more about this. As I mentioned, this is before anything. Each one of these, each particle, represents a possible state. Now, right now, I'm only drawing a particle as representing position, but it can also have more dimensions. It can represent velocity, height, color, whatever you want it to represent. It can represent, it can be a multidimensional quantity that represents all of those things. Okay, so initially we're going to scatter a whole bunch of particles uniformly throughout our state space and say these are all the different possible states or approximate states that the system could be in. Next, we're actually going to make a measurement. And after the measurement, we're going to assign importance weights to each of the particles. So let's continue this example down below. We have the same particles, And now I'm going to assign importance to each of them. And I'm going to do that by making them larger. According to their likelihood, particles will be large or small. So how do we assign these importance weights? Well, we go kind of backwards from what you might think of with some of the things we do before. That is, we're going to take each particle and we will simulate the measurement that would have come from that particle if that had been the actual state. We will then compare it to our measurement, and inasmuch as it's close to the measurement, we will give it a higher state. If it's far away, or higher weight. If it's far away, we give it a lower weight. Okay, this bears a little bit of repeating because it's very, very important. So the importance, in this case represented by the dot size, corresponds to how likely that our actual observation came from a system that was in the state represented by that particular particle. So you can see right away the downside of this is when we make an observation, instead of just applying a matrix update like we did with the Kalman filter, we now have to simulate that observation for every one of our particles. There may be thousands or more. So this is a little bit more computationally burdensome, but it works beautifully. Now perhaps I could share just a brief story. When I first started learning about particle filters, most of the articles about it talked about ways of making them very efficient. And these articles were very hard to understand without an understanding of, an explanation of the basic idea behind the particle filter. And I spoke to multiple people who I highly respected who said they couldn't make heads or tails of what this idea was about. It's actually very straightforward. The difficulty is in the implementation. It wasn't until some years later when I was watching a lecture by somebody in computer science who just created an object that represented a particle in Python, created an array of 1,000 of those, and then just proceeded to run through the particle evaluation in a loop. And it turns out on a modern processor, it's still pretty fast, as in almost no time at all passed. So it's easier, I think, than it might look right away, but it is definitely more computationally burdensome than a Kalman filter. Okay, so now we have our weights corresponding to particle size. The next step is going to be I think the most critical part of particle filters. It's called the resampling step. So after we've done this, we resample. And everything so far that we've done computationally can be done in a multi-threaded system where each particle is operating independently. We get a particular observation. Each particle evaluates how likely it is that it produced, its particular state produced that observation. But now we're going to go through and we will select which particles to keep. And so we choose with replacement particles based on their likelihood or their weight. So in this, more likely particles, or particles with a higher weight, are going to be are likely to be chosen many times. So there's an efficient way of doing this called the wheel method. Let me see if I can represent this well. Okay, so we have a wheel, and each particle is given space on this wheel. Likely particles, or particles with high weights, are given lots of room. Unlikely ones are given less room, and so on around this wheel. So it comes down to this. We'll have different particles, and call this alpha 1, alpha 0, alpha 2, and we're going to pick these alphas. Alpha I is equal to the weight divided by the sum of all the weights. Particle weight from our previous page. So then the sum of all the weights is, or the distance around as we go around the circle, is going to be 1. So here's the procedure. First, we take a random step and we'll select the particle we land on. So if we start here, for example, we are much more likely to land on a particle that has more space on the wheel. So here's our random step, and this would be our first selected particle. And step 2, we repeat. When we reach the end of the particles, we just wrap around and we continue. When we pick a particle, if we're doing this in software, we would add that particle to an array, and we may actually use the same particle multiple times. So if this was once again in software and a particle is represented by an object, we would have to duplicate that object, and you'll see why we duplicate it in the next step. So now we've selected a bunch of particles. In this particular case, alpha 2 will be picked more often than alpha 0, and alpha 3 might not even be picked at all. It was right here. Same with alpha 4 and 5. So some particles may not be picked, and some particles may be picked multiple times. So going back to our previous example, at the end of this step, it's going to look effectively like this. We we will have multiple copies of these particles, maybe one of these, but for the most part, the number of particles that we have is going to be related to the weight in a random way. So we'll end up with something like this. We can choose how many particles we have. Usually a large number is chosen at the beginning, and we keep the same number. But once we've found the object we're trying to track, if we're worried about efficiency, we could actually use fewer particles. So the next step is where we apply our model. This is like the prediction step in the Kalman filter. So we're going to move all of the new particles, or the chosen particles, however you want to put it, now when we did this in a Kalman filter, we did x of n plus 1 is equal to a times x of n, and we did not do the noise. But in this case, we're actually going to include the noise, and it turns out it's going to be very important. So for each particle I, the state at time n plus 1 is going to be whatever our nonlinear function is of the state at times n plus the noise. So it's very important that here we actually generate noise and add it in. And this is what is going to make the difference between, or this is what's going to differentiate all these identical particles. Because, for example, right here, we have 5 particles representing the same state. But each of these particles will have a different noise added to them, so that after we do step 4, we will now have 4 particles, or 5 particles that represent similar states. Each one has been affected differently by adding in different noise. Okay, so here's an example. Suppose we had one particle that had an associated position and a velocity illustrated by that line, and it was a very likely particle, so we ended up choosing 4 copies of it. What happens after this step? Well, if that was our original particle, we will now have 4 particles that have moved in roughly the same direction, and now have slightly different states, slightly different position, slightly different velocities relative to each other. So that one particle now became 4 similar particles. So how would this work with our car bench tree example? If our model had built-in motion, then every particle here would have some motion. Initially, that motion would be random. So some of the particles would move left, some of them would move right. The particles, if the car moved to the right, the particles that moved to the right would be very likely to be picked next time. The particles that move to the left are now nowhere near the car, so at the next iteration they're going to be unlikely, and therefore they won't be picked, or they won't be likely to be picked. With the bench and the tree, some of those particles will move to the right and some will move to the left. Some of them then will move outside of the range of future observations of the car or of the bench and the tree, and so will die out. Some will remain perhaps in the range and will be selected, but it will be a fewer number of them. This is kind of like gravel on a busy road. Every time a car drives over it, the gravel jumps around. But as long as it's jumping around in the road, it will continue to get disturbed until it makes it over to the side. As a result, the roadway remains clear of gravel, and the gravel just goes off to the side where cyclists get to deal with it. In the same way, we will have particles that are bouncing around the bench and the tree, but they will become less and less, and as they bounce out of the way, they will disappear. So that in steady state, there may be few or no particles associated with the bench or the tree, and all the particles will be associated with the car. So how does that happen? Well, since we've normalized the space that each particle takes up on the wheel using this alpha equation, as some particles become less likely, the likely particles will take up increasingly more space on the wheel and be more likely to be chosen. So in this particular example, I showed that the most common particles were chosen 5 times. They may be chosen 20 or 30 times going forward, and so we get this nice little cluster of particles that are going to follow the moving object. So what happens if that bench stands up and starts to move? Well, if there was still a particle there, it will likely replicate and start following the bench. However, sometimes the particles may all be gone, and now we've lost our bench. So one thing that we want to do is occasionally redistribute particles to make sure we catch things that we might have missed. So let me summarize some of these observations and make a few more. So the first observation is what we just said about redistributing particles. This can be done by taking some percentage of the particles that we have and randomizing their states once again. Another thing to notice, and this is very related to the Kalman filter as well, the measurement step always tightens our state estimate, and the motion or model update step tends to diffuse our state update. Likewise, when we did the Kalman filter, our prediction step increased our uncertainty, and the measurement step, no matter how noisy it was, still decreased the uncertainty. And one more observation here is that particle filters seem almost miraculous in how they work. But they're only reasonable for a relatively low-dimensional state system. And the reason for this is we need to have enough particles to represent an approximate distribution of a system. In one dimension, maybe that's 30 particles and we can get a reasonable view of it. But once you go up to a 3D space, we have to represent this distribution in 3 dimensions, and we're going to need many more particles. If we were to go up to a 6 or 15 dimensional space, the number of particles grows tremendously. And so in that case, using a Kalman filter or extended Kalman filter is going to be much, much more efficient.